G'day guys, been doing a little bit of experimentation on some ferrite pot cores, and the reason for this is to make a high powered pinpointer that you can just put on a piece of cable, and if you wanted to carry it with you, you could put it on your detector and poke at the ground. If you didn't know if it was a big metal target there, and you can't get your coil into the hole properly to measure exactly where it is, and you're just digging some huge hole when maybe it's only a very small target in the side of the hole, you can make something like this up, and it would narrow down your search time. But there's a lot of configurations of something like a pinpointer. The battery powered ones are pretty well, they are low powered, otherwise they flatten the battery very quickly. And you can knock one up yourself very easy. Now this is just an experimental one I've put together using a pot core. Normally you would not use a pot core, you would use a ferrite rod out of an AM radio, believe it or not. And I think in Russia they were making ferrite rods that were about 8 inches long, and that is what I would classify as the best material to make a pinpointer from if you want to stick it on your detector. But anyway, give you an idea, um, this is basically a similar version to this thing here. That's actually out of a Minelab detector power supply, and in the middle there would have had a plastic bobbin. Actually, I've got a plastic bobbin here. The plastic bobbin, you would wind your wire on this former, and it would go in here, and that would go in there, and you would have your winding around the bobbin, and 2 wires or whatever. You can put lots of wire turns in there if you want, but yeah, you'd have your 2 wires come out and you connect it up like so. I have an extra resistor on here. It's only I think it's 820 ohms. That's just to calm things down a little bit. Normally the damping circuit within the detector will dampen things nicely, but as you can see here, I'm not using very thick Litz wire. It's very, very thin, and the reason being that it's so thin is because when you use ferrite, you don't need as many turns as making an air coil, and it increases the inductance massively by using ferrite. But I'll give you an idea. We'll turn this thing on. It'll make a horrible noise at the moment, and I'll explain why it does that and how to shut it up. We'll put it on. I'll better turn this up a bit so you can hear it. Okay, it's sitting there working away. Now, if I get a screwdriver or something, like so, so you get a very concentrated, well, this is basically, the way I've got it connected up, I'll call that leakage inductance, because I've got the core gapped with bits of paper. The core is not hard up on itself, and you actually have to do this. You need a very small air gap, because these detectors put out a unipolar pulse as such, and it doesn't have what they need is what they call a reset mechanism. If you had a square wave that was like up, then below zero that way, and it was all equal, the crystal lattice structure inside the ferrites, that's how they're constructed, will flip domains and it will balance out and it won't get hot. If you want to put on a very few amount of turns and have this as a complete push together seal thing, the inductance will go very, very high and it basically won't work properly. You have to air core the inductance or the ferrite to lower the inductance. It makes an air gap in the magnetic path and the inductance comes down and these things behave properly. The other way you can do it is you can use cores like these. These are iron powder cores. The only trouble with iron powder cores is you do not get much inductance per turn, and if you wind the wire on, you will not get up to 300 odd microhenries on that core. You'd have to use the most thinnest of hair wire, then the resistance would be too great that it will go pear-shaped. This is one here. I made this up ages ago. This is on a ferrite core, and I've used a medium sized Litz wire, not the same as in the coils, but a lot smaller because I didn't need the resistance to be like, 0.1 of an ohm or something like that or less. And on this core, I've wound it whatever amount of turns was there, and if I put that on the inductance meter, that'll indicate 300 microhenries, and it will be roughly about 0.2 to 0.5 of an ohm. So that works for testing. Like if I just wanted to test a detector on the end of something like this on this cable here, I could use that, just to test mono detector. And it's still enough leakage here where you can get small targets and test. The thing is, when you use this, it's so small, it's not going to pick up much interference. So you can use very, very small targets and, play with your detector, optimize it to see how sensitive you can get it. It's even good too when you're working on the electronics inside the detector. You can try various changes of components like the filters. You can change the capacitor values and so forth. And, you can move a target of a small bit of gold or whatever near this. And you can just see if there's an improvement. But like I say, it doesn't pick up much interference. So maybe out in the field you get a different result with interference. Maybe those capacitors are removing some interference and you've made the detector more sensitive and it's going to get more interference. But like I say, a lot of this stuff is suck it and see how it goes. Now with this one here, I'll pull him apart. I'll show you how I made it. You don't really, like I say, you don't really need this resistor here. I've just done it to dampen things down. It was just a bit too grunty to say, use a word, but I'll pull it apart. You can probably see on this pot core where the bobbin slides in, and I've got bits of paper stuck on the core to cause an air gap. You only need an air gap of a couple of thou of an inch. You don't need much of an air gap. It all depends on how many turns of wire that you put on the core to get your given inductance. Actually, I wound enough wire on this core here to give me about 500 microhenries of inductance. And when I say that, that was with this core with no paper on it, closed hard. It would give 500 microhenries of inductance. When I started to put paper between the core halves and separate it, I did that to a couple of thou of an inch odd or so, and that dropped the inductance down to 300. That's what the detector likes to see, to keep it all very happy. And when it gets there, you put paper or whatever. Paper's a good thing to use. You don't want to use anything metallic because it won't work. And paper's good because you can keep putting paper in there. It doesn't compress much. And when you get the right value, with these cores here, I don't know if you can see in the middle, hang on a sec, I'll just get rid of the paper I put on because it's in the way. It's double-sided tape. But yeah, these things are just called pot cores. The material I think is called N27 or N28. All manufacturers have their own codes and that, but I think N27, 28, it's either Phillips or Ferrite cube. I can't remember which one. But anyway, you can see in the middle is a hole, and the hole in that one as well. And what you do with these to keep them stable is you put, preferably, no, absolutely, a nylon nut and bolt through it. Do not put a conductive metal nut and bolt through the middle of it. Just tighten it up enough so it stays together. Because what happens, I'll give you an idea on this one. I'll take the paper out. The inductance will go sky high, but that's why I have this extra resistor here, because when the inductance is greater and I'm opening and closing the core, you could get excessive voltage spikes, and it may get past the internal damping circuit in the detector. I'm playing it safe. So there was an 820 or 880 ohm resistor or something. Not critical, just don't go too low because you've already got a 330 in the detector and you don't want to upset that too much either. Hang on a sec. I had this set up so I can go through the one side hole there. I'll just give it a couple of twists around like that. Okay, I'll put this back together like thus, and there's not much of a gap there, and it'll squeal. You have a listen to this. The whole thing will rattle. I take it you can hear that horrible squealing. I'll turn the detector audio. Yeah, it's you can hear that. That's the pulse of the detector. That's the transmit pulse, rattling, literally rattling the wires. You know, somewhere around 15, 20 kilohertz or so, whatever it's doing at the moment. Because these things have different size pulses, you can't really give it a frequency. It's you know, it's a time period of pulses. But anyway, let's have a look at this. Now, if I touch it, it'll go crazy. Now, if I push hard on it, hear that? It stops making that horrible sound. So that's why you've got to keep it tight. That's why you put a nylon nut and bolt through it. But anyway, we'll see what it's doing. It's probably the detector will go nuts. Yeah, it will be. It's too much inductance there. The detector won't like it. So I'll open this with my hand very slowly. There you go. The detector, I'll turn it up so you can hear it. But what's actually happening is I'm holding it with my fingers and I'm moving it very, very, in very small amounts, just by different compression of my fingers, and that'll make it go crazy. That's why you got to put paper in there and lock it up. So you could use it as it makes a very good pinpointer just with the leakage. You know, it's a hot rock. You could locate your hot rocks down to a fine point, or you know, something metal. So that would make a very good pinpointer. If you wanted to do this, you could probably enclose the whole thing in resin and put in a bit of PVC tubing, and put a PVC tubing end cap on it, one of the rounded ones, and yeah, you can use that as a very deep going pinpointer. On a decent sized piece of metal. Like, this is getting ridiculous, but I'm going to do it anyway. Like, I've got a can here, right? Like, So I'll turn it off because it's making a lot of noise. But you know, a normal pinpointer won't give you that distance, and you can do this, like I say, extra winds on it to get the inductance up, air gap it to get the inductance back to 300, and it'll work like a charm. If you're doing cores like this, these won't work. You can't use it as a pinpointer. It's in a completely closed magnetic system, and there's very little leakage from these. They're designed not to be have much leakage. These are also designed not to have much leakage, but they do, because I air gapped it quite a bit, and magnetic flux will escape out of the hole there all the way around. Depends on the frequency, of course, but for the detector, it will actually do that. Now I'll just have a look at this pot core. This is a different one than the other material I said, but it's the same. It's exactly the same grade. It's got T22 and two something or other, and I can't see it. Light's shining off it in my eyes. 250. But anyway, that's a pot core. Most of the pot cores are a particular type of ferrite. There's zinc ferrites and manganese ferrites. The easiest way to tell what's what is you can just put on a couple of windings, measure on a LCR meter, such as one of these ones. That's it's got inductance on it. You know, if you turn it on, you'll see here it'll read H for henries, but it'll put an inductor in there. It'll come down to microhenries. You know, even a bit of wire on it like that will probably give a reading. If I short it, it'll say, oh, that's a bit of an inductor there, and that is 2 microhenries. 1.8. It'll move around a little bit because I'm moving around, but give you an idea. You know, that you could use that loop as an inductor. 1.7 now, and yeah, open circuit. Yeah, so that's that on this. This is just normal any old coil cable, standard coil cable off a mono coil. You have an old mono, you know, standard configuration. Like I say, if you wire it up with a better core than what I used, I mean, and that wire is a bit thin. It really is. I think I had about 1.7 ohms of resistance there. It's not really the best. You want to get down to about an ohm or half an ohm. Half an ohm, you know, is what standard coils are. So, you know, I use this Litz wire here. It's 0.04 by 20 strands. It's very, very thin. But normally I would use, on something like that, I should have used this Litz wire here, which is 0.05 by 120 strands. So that's actually very good. You can use this stuff for anything. And the standard wire, I haven't got any here. It isn't, you know, it's a lot thicker. Standard Litz wire for these things is about a millimeter or a little bit over 1.1, 1.2 in diameter. Anyway, that's this one. I can just quickly hook this one up. Why not? We'll hook it up, unsolder the other one, and give you an idea on how the difference is. Whoopsie! I just banged the camera. I don't know if it made any difference to anything. I don't think I need that resistor there either, so we'll take that off. Oops. You clear my iron up, it's a bit dirty. There we go. Oops, that re-stuck. The thing with Litz wire too, when you solder Litz wire, because it's every strand's insulated, keep the iron on it for a long period of time and flow flux and solder onto it, because I have noticed on occasion that you think that you soldered the Litz wire. All it's done is the outer um, uh, strands of the Litz wire, and the inside ones aren't tinned up. They're not conducting any power, which means you have a power loss for your cable because you just can't deliver the power. You haven't got enough strands, so it's got higher resistance. So always cook your Litz wire. Even here, this one's broken a few strands because it's been wiggled on and off. So it's only one or two out of probably 70, so it's not going to make that much difference. But it's just one of those things you've got to be wary of. And the insulation on Litz wire too. Usually it's a polyamide type insulation, and it self-fluxes, but you've got to get it up to about 400 degrees on your iron. I did that before, and I don't like doing it for a long time. It wrecks your soldering iron. It overheats everything, so it probably doesn't last as long. Anyway, we've got this one here. This is what I use for testing. Oh God, it's got a few loose windings there because I've never taped it. Normally when you do this, you'd run tape around and around and around the toroid to lock everything in place. So this probably screamed too, we'll see. No, didn't like that at all. Why didn't it like that? Ah, okay. I must have changed something from last time because it's telling me it's a coil overcurrent on that particular one. Maybe I had it on double D cable before, which is less resistance, and this one here, as it's a mono cable, I probably haven't got the right inductance on this coil, I would say, or maybe it's too low in resistance. I can quickly find that out. Make sure I did turn the detector off. I don't want to unsolder it while it's on, banging around in overcurrent mode or something like that. It could cause all sorts of disasters. But let's have a quick look and just see what this one's sitting at. Okay, get the inductance meter. I'll put this on inductance. I will put it, I can leave it at 1 kilohertz, doesn't make any difference. And because I'm not measuring very small inductances, I can actually hold this with my fingers. It's not going to have much effect. So we'll have a look and see what it says. 196 microhenries. Hey, what's happened here? We're missing 100 microhenries. No wonder it didn't work. That's very strange. Did I need some Litz wire, and did I chop some off it? I might have done. But yeah, that's too low. No wonder it doesn't work. Bugger. So that obviously had more turns on it. Maybe I've got another one somewhere or this is the wrong one. Maybe this one was for a different project, and I don't know. Things are being put away here. Oh, here we go. I'll give you an idea here. Come here, you. Okay, you can use this. One of these things, right? This is a Murata 1430433C. That's what it is. And that is a open ferrite bobbin type inductor, but it's 300 microhenries, I'm pretty sure. We'll just have a quick check on that. Because what I'll do with this one, 312, close enough. It won't make any difference. 320 down to about 280 doesn't make any difference. Okay, let's solder him on. And I actually haven't used this one. in this situation, like as in a test for this or anything like that. We're going to find out how good it is. It's going to have plenty of leakage because it's not an enclosed structure. It might make a really good pinpointer. We'll have a look. I think I might need some more solder on that. It's not melting very good. Some flux. I'll put some more solder on that. Hang on a sec. Let's put some on there. Please go on there. And yeah, a bit more there. See how these, I'm putting solder on, it's getting very blobby. You shouldn't do that. That makes a reactive target because it's a big hunk of metal. Oh, why you want? God, this thing's starting to cook my fingers now and it won't get hot enough to melt the solder. What's going on? Hang on, here we go. Yeah, don't do what I'm doing with those big blobs there. That's really, really bad doing that. But just for this, we're going to do it. There we go, finally melted. Okay, so we got this Murata core. Look at that. Nice and neat, better than my ones. Machine wound. Now this detector should fire up, no problem. We'll turn up the volume. Oh, there you go. Now, I don't know the how this thing's put together in regards to its resistance. It might be really low, but the detector sounds desensitized. Oh no, hang on, have a listen to it. It sounds desensitized, like it's not picking up anything at all. But if I get really close to it, actually that core doesn't work properly for doing this. I think it's the okay, I'll tell you exactly why. It's wound in enamel wire. It's not Litz wire. Okay, and the eddy currents aren't decaying fast enough and getting out of the receiver. It's desensitizing the receiver. That's what's happening, right? But is that a benefit? And why I say that is because there's no interference, there's no reaction around it. But when you get a target and get close, like right on it, like a normal pinpointer, right? It does work. I'll put it in enhanced mode. The whole thing will probably die. Won't be able to handle the very fast switching waveforms that are in enhanced. Let's see. That's interesting. Works even better. Now, isn't that funny? It's an enhance. In normal mode, it's deaf as a post. And I would have thought, logically, that in enhance, it wouldn't have worked at all. I thought it would have totally gone crazy. But let's see how far away I can get. This is interesting, this. Okay. So if you want to get a Murata one, just make sure you use it in a faster switching mode like enhance, or actually this is 5000. We can put it into fine gold, see if it still works. Yep, works in fine gold too. Not as good as enhance. I'd say that fine gold, the receiver's coming on much too early after the transmit pulses. But I thought enhance would work the same way. But there, you can make a pinpointer, a deaf as a post pinpointer, and it'll give you really good depth on that. The only thing is when it's in we'll call it deaf mode, does it ground balance? Now that's an interesting one. I'll put it in tracking and I'll put it back into fix and into tracking again. lo and behold, I don't expect it to cancel out a hot rock, which is the size of the whole bobbin, winding and the whole thing. But yeah, massively diminishes it. You know that wasn't a metallic target. You know, soft, horribly soft. So you'd say, oh, that definitely is something else. I'll just try a little tiny nut off a switch. We'll see what that does. Nah, be no good on small targets like that. So it's desensitizing the detector. You know, on something about that. Yeah, but that core, this core here, if that was unwound and rewound with a thicker, actually, I think this one here, the 0.5 by 120, I think if it was rewound with that, would actually work quite well indeed. I don't usually use this style in any of my electronic work because it does have leakage around it, and it will get into other parts as soon as, you know, pity that wasn't bigger, I'd slide it on. But yeah, with pot cores, very interesting things. Here's a real big pot core. This is a beauty, this one. This has a permeability of 9,500. And what I was actually doing with this, I was actually making a transformer for the input of a metal detector to step up the signal level. These cores are extremely low loss. There's next to nothing lost. And yeah, I was just, this is from an experiment I was doing a while ago. As you can see, they're the secondary output, and this is the, oh, there you go, standard Litz wire. So yeah, like I say, here's the size difference in standard Litz wire, which we use for coils, compared to the one I had on that inductor. You can have a look at that. It's much different. And the one I wound, that very small pot core, you know, if you want to compare it, um, you know, it's massively thinner than coil wire, massively thinner. So yeah, you could probably you don't want to make a pinpointer out; it's too fat, too heavy too. Ferrite, this ferrite material is quite heavy. It's like it's, you could basically say it's nearly as heavy as metal, but not quite, you know, as iron or something like that. So yeah, if you really do want to make one of these, you know, you could probably get that and wind it with Litz wire, because I just noticed that it is just standard enamel wire. It is way too thick, and it's going to retain eddy currents generated, and it's going to fall into the receive window of the detector and desensitize it, which it is doing. But maybe I'll get one of these and I'll rewind it in Litz wire, and we'll see how good it goes. I think it'd be quite good. You put that one in a plastic tube, I think you'd probably get 10 inches as a pinpointer out of it, maybe more. Like I say, if you don't do it, you don't know. So, hope that's been of some use to someone. But if you can get the Russian ferrite rods, you can probably get them on eBay. And when you buy them, they're cheap anyway, right? Don't buy one. Buy a 5 or 6, because I guarantee you when they come, they're going to crack some in half. It's very brittle. But if you put it in a PVC pipe, wrap it with some foam or something, it's fine. It'll last forever. And all you do is just wind the wire around. You need a lot more turns on it because it's an open-ended structure, but it's more stable, and it makes a really good pinpointer for these detectors. It's probably, you know, a lot of people are thinking, oh, look, you know, I've got my little handheld one I keep on my belt or whatever. Yeah, great, that's fine for little tiny holes. But you know, if you know, say you're out there and you're running a big coil, you know, 16, 18 inch or something like that, and you get a target, and you know, you don't know exactly if it's really, really deep or it's intermediate, and you know, and you've got a normal pinpointer and it's not showing, it just hasn't got the grunt to show you where the target is. It just can't get through the you know, a big thick layer of ground. Something like this it will punch down and give you an indication. So there's a lot there for another day too. I can get some more cores and wind up some more bobbins and some of the rods, and we can test them out. And I'll show you how they go. Unless you want to do it yourself, you can do it yourself. Just get an old, you know, crapped out mono coil, chop the thing off, and you just got 2 wires, solder it on, away you go. If you experiment around though, you should have an inductance meter. If you don't wind on enough inductance or too much inductance, you know, it may possibly have an adverse reaction. It may generate too much of a back EMF spike. It may want to try and draw too much current out of the detector. There's mechanisms inside the detector that protects it. Like if you put a short circuit on it, not that I would, but you know, you've probably all seen it on the displays if you're using the GPX detectors. It comes up with coil over current. Well, that's basically what it is. You know, it's you know, it's too much load on the detector from the coil, or something's gone a bit, you know, skew-if, and it's triggered the detection circuit. So you know, it will shut down and not sit there and destroy itself. So that's a good thing, you know. Minelab have put some good safety features in these detectors for their own protection. I've also noticed that if there's anything goes wrong with the internal electronics and it doesn't switch properly, it turns the receive input FETs off, so you don't have anything coming in and blowing up your front end op amps inside the detector, which the ones they're using now are very, very expensive. They've all gone way up in price, and it won't just take out the op amps, it'll take out the MOSFETs, it'll take out probably, you know, the oh, whatever it is, the quad pinned dual MOSFET, the one that supplies bias current to the op amps when it's in the transmit state. You know, those things will probably blow up, and you know, have a lot of work. It's very fiddly to repair, and you know, you're up for probably $50 of op amps now, and yeah, and yeah, all the hard work of pulling everything else out, or desoldering it when it's glued to the board as well. Got to be careful, and replacing it all. So yeah, that's a good thing about Minelabs. They pretty hardy little beasts, but that needs some work. That's commercially made, and I think I got that for a power supply project or something ages ago. I can't even remember what I got it for, but 300. Yeah, I don't know, but if that was rewound in Litz, it would probably work very well. Damn it, I'm going to do it. I'm going to rewind it in Litz. I'll save it for another video. And we'll see how well it goes. It should be an absolute ripper. We'll give that a go too. And in the meantime, in the garage, I'm going to try and see if I can hunt up some ferrite, AM ferrite rod material. Not at a little handheld transistor radios because it's not big enough. You really want the long ones. They're about 8 inches or 10 inches long, and you know, you can you know, get a really good magnetic field on the ends, and it worked really good as a pinpointer. Anyway, that's enough waffle. I've got to remember to turn my audio amp off. Click. And yeah, I'll do some more and put another video up just for the fun of it. Catches.